So he's like a long-term speaker for our NCTS-iTHEMS workshop. He gave, we have 3 workshops, so he gave 3 talks. Hopefully he can continue next year. Yeah, and he is also a visitor for Riken. Last year he stayed in Riken for several months when I was gone. And he also have a visit this year for the workshop hosted by iTHEMS. Let's welcome him again.
Yeah. Thank you, Tsing, for a very nice introduction. Yes, and I'm very happy to present several times here. And then I hope this is the new thing, so I hope you will not be bored by my previous topics. So this is what I'm trying to bring to you is the bridging between the condensed matter physics and the quantum information. So my training is condensed matter theorist, so I'm trying to learn quantum information from this project. And it's based on these 2 papers. And, let me see, okay. And then these are my collaborators, Sam Crew, who's very brilliant, postdoc now moved to quantum computing company. Yinlin, and then Hensi, Yinlin is my student, Hensi is the audience right now. Okay, I'm also want to show that I borrowed this topic from a very nice book by famous people. Quantum information meets quantum matter, and it's available publicly in the archive. So I think you can learn from both sides. It's a very nice book. Okay, so now I just go to my topic. So why as a condensed matter physicist, we are trying to understand many-body quantum physics. So why it's related to quantum informations? Because as was a student that strongly influenced by Xiao Gangwen's lectures, so we are basically thinking about if there are 2 inequivalent quantum matters that belong to 2 different classes, they cannot be connected by finite depth local unitary circuit. So that's how we can connect quantum information to the quantum condensed matter. So let's suppose I have a quantum matter A with some, for example, local spins, degrees of freedom, and then we can use some finite depth local unitary circuit that construct a state which belongs to quantum matter B. If this is finite depth, then we are saying these 2 quantum matters are the same. Okay? So with this concept, then we can ask about the phase transitions, and then in terms of this language, if quantum matter A and quantum matter B belong to 2 different phases, then I cannot construct such a finite depth local unitary circuit. So it's relevant to the condensed matter setup because, as we know, there are several Hamiltonian models that we can describe that has a phase transition that basically say there's a phase A and phase B, and then if I want to tune some parameter from A to B, there's some quantum phase transition happen. So one interesting example is this kind of spin liquid. So suppose you have a Heisenberg Hamiltonians on some frustrated systems. So of course you can know on one side they can form a valence bond crystal, which is a short range entangled state. On the other hand, if you tune to this RVB with a lot of resonance superposition liquid state, it's a long range entangled state, right? So you know there must be a phase transition, and then there's no way to construct finite depth local circuit to connect this phase, this valence bond crystal phase, to the RVB phase. Okay. So with this picture in mind, then we can think about how should I use quantum information language to understand critical phase. So since I need infinite quantum resource to connect these 2, then you expect the entanglements must diverge at this point. So that's what people can use this entanglement as a tools to study phase transitions in this many-body setup. Okay. So now people are pushed more because we know there's a lot of different quantum resources, not just the entanglement, that can be magic, which I will be described very soon. And then other things that can also detect these many-body phase transitions. Okay, so there's a scalar resource, which is some kind of entanglement entropy quantities, and then there can be some kind of a resolved spectrum, which we call it the entanglement spectrums. So I will show you that this type of quantum resource can be used to diagnose many-body phases and then their transitions. Okay, so of course entanglement are well known, and as previous speakers described, it can also be applied to a non-equilibrium phase transition, monitored induced phase transition. So now I'm trying to do the other way around. I'm using a different quantum resource measurement to study the equilibrium phase transition. So now today I will show basically two. One is the magic, which is the non-stabilizerness, and then the other one is the non-Gaussianity. Okay. So just a very simple discussion. So as we know, entanglement as a quantum resource, we need to define what is the free state, which is very cheap. So it's a separable state, and a free operation. Basically, you cannot increase entanglement. So it's a local operation, classical communication, and then source is this kind of non-local correlations of the state. So magic, that's what people are investigated, is this kind of non-stabilizerness. So you have a state which is free, we call it a stabilizer state, and then the free operation which cannot increase the non-stabilizerness, we call the Clifford circuit, and then the resource we'll call it non-stabilizerness. So far it's just a terminology. So there's more content I will show in this slide. So the Clifford gate I am defining here is a very familiar one for most of you, I guess. For example, this Hadamard gate, the phase gate, and then the CNAT gate. And then we want this to fit this resource theory. We want to have a quantity that is resource monotone, meaning that if I have a state X by these Clifford operations, that cannot increase this non-stabilizerness. And there's a more mathematical structure. You can write it down. For example, you can define the stabilizer state as a product of this computational basis, zeros by these Clifford unitaries. And then how do you define Clifford unitaries? Basically, it's map one of the Pauli strings to another Pauli strings. Okay. Yes, please. Okay, so I speak too fast. So in here, free state is defined by this one. This is the free state. This is the stabilizer state. By definition, is in here. The gate is not. So this is exclude the magic gate. So there's no magic gate for Clifford gate. So I only contain this Hadamard phase gate, CNAT gate. There's no arbitrary phase gate, magic gate, T gates in here. Yeah, I don't have T gate in here. So it's a very simple gate. And then there's a theorem, Gauss-Kernel theorem, saying that for any stabilizer state, it can be efficiently classically simulated. So it's just a quantity that's quantify how hard you can simulate using the quantum computer, a classical computer. So for any stabilizer states, since you can use this Clifford gate, which is somehow some specific point in the block sphere, so you can just label this point on the block spheres by using classical bits. So it should be efficiently classically simulable. That's some kind of a very naive idea. So if you can operate using a universal gate operating on arbitrary point in the block sphere, it cannot be easily simulated using the map to a standard bit. So it will be harder to simulate. Some naive argument. So you need to find a way to quantify how hard to classically simulate. So that's why people want to define this. Just like how you want to define a quantity that's describing how a state is entangled. So So people invent this entanglement entropy. So there's a quantity that you can quantify how hard to simulate this, or in terms of distance, how far away it's a non-stabilizer state is away from the stabilizer state. So this is what people define some quantity. So one of the quantities is called the stabilizer Renyi entropy. So it's a good measurement proposed by these people. And it's a relatively easy way to compute, because you can have some polystring. I just using a different a presentation of my polystring using the binary index A and B. And then you can just, for a given state, you just evaluate the set of your polystring, so you get some probability distributions. So since it is a probability distribution, you can evaluate the associated entropy for this probability. Then, as you know, if this is peak at specific point, meaning I only have one polystring is 1, others are 0, then the associated entropy will be 0. And then since it's only for a specific peak, so you know this state just fixed on some many n-qubit plus sphere. So it should be classically easy to simulable. On the other hand, if it's very broad spectrum, then it must be some kind of superposition of all possible strings, and then it will give a very large entropy measures. So it's a way that people define for quantifying the non-stabilizerness. So it's called a stabilizer Renyi entropy. So this subtraction is just trying to make the stabilizer state to have 0 stabilizer Renyi entropy. And then I just give you some examples. So of course, magic state, which is not a stabilizer state, so it has non-zero. M2, so when I say M2, meaning I've taken the second Renyi of this stabilizer Renyi entropy. Bell state is an entangled state, but of course it's an entangled, but it's kind of classically simulable. So it has a 0 M2. And then you can use this to many-body state as well. And then people already use this SRE to study best transition. So this is one of the paper by the same group. So they show at the transition point, it basically goes to the extremal values of this SRE. And then for the gapped one, they have a smaller value. So, okay, so we're trying to do this thing for a more exotic many-body phase is called the gapless or gapped SPT phase, the symmetry protected topological phase. So, of course, this is a different subject that I will not really jump in, but for a very short definition, so for SPT phase, it's a phase that cannot be simply classified by a local order parameter, so there is no symmetry breaking pattern that you can associate with this SPT phase. But on the other hand, you can use the non-local order parameter to clarify this phase. Okay. So I just show you by examples. So this is so-called the cluster SPT phase. It's protected by the symmetry Z2 cross Z2. So Z2 in the odd side and Z2 in the even side. So you see this is the Hamiltonian, and then where H is less than 1.5. Sorry, 0.5, it belongs to some topological phase, and then it exists to 0.5 trivial phase. And the transition is at H equals to 0.5. Okay, so there's some interesting unitary map, basically by the CZ gate, the product of CZ gates basically will map this term to this term. So there's some kind of duality mapping by the CZ gate, and then this is the non-local order parameter associated with this SPT phase. So you see this is some kind of polystring for the non-local order parameter. So I'm trying to analyze their probability. Basically, we refer it as a polyspectrum which associates with this SRE. So this is the result. So if I compute the M2, which is the secondary entropy, basically I cannot distinguish the trivial and the topological phase. They are the same. Why are they are the same? Because there's some duality transformation by the CZ gate, map one of the string to another string. Okay, but however, it can detect the transition that basically has a non-analytic form at the transition point by tuning this parameter. And then if I look at the associated probability distribution, basically we refer it as a Pauli spectrum. We show this associate string, so this is the SPD string for the topological one, and then the trivial string that's associated with trivial one, and then they have duality map by this control Z gate. Yes, please. Okay. So this one, how from the definition? Okay. So if from this definition, if this distribution is picked, right? So only one other are zero, then that indicates this state must fix on some. Di is a Pauli string.
So okay, and you sum all
I, so if I have n qubits, I have 4 to the power n Pauli string. So each of the sides I have identity x, y, z. So I have 4 to the power n combination. So it forms a probability distributions if I evaluate this Pauli string.
So for so this is a measure for the magic.
Yes, this is the people measure for magic. Yeah. Yes, so if it's non-magic, it's a stabilizer state. So what I'm saying, if it's a stabilizer state, then you can consider this psi will basically pointing in one of the n qubits block sphere. So indicates for a specific, there will be a specific value only for one Pauli string, but other will be zero. For example, if you consider one qubit pointing along the north pole, then it's be z, and then it will be only one, but the other will be zeros.
So in order to prove the monotonicity,
Yes. That will be, yeah, it will be non-trivial if you consider non-monotonicity. Yeah, no, I think you can do the magic distillation as well. So you can do n copies, and then you do magic distillations, and then you can analyze the non-monotonicities from this process as well. So you don't need to map to the magic to the entanglement. You can still use magic. Yeah, and then you can also trying to do a simple way. Just apply the Clifford gate, and then you can show this any arbitrary Clifford gate cannot increase this m. So because from a pure state, it just map one di to another dj, so it cannot increase. So from operating the Clifford gate, you see the M2 cannot change at all.
So is it possible to map this to because the monotonicity of entanglement entropy is well known and very much difficult to prove. But I think this one is very.
It's relatively hard, so people, so naively people use some convexity theorems to do, or some optimization methods. So you can define it. And then I believe for this stabilizer Renyi entropy, so far it's only proof for alpha less equal than 2 is a monotonic function. For alpha greater than 2, I think it's non-monotonic. For mixed state. For pure state, I think it's monotonic, but for mixed states, alpha equals greater than 3, you need to use another quantity. But alpha less equal than 2, I think even for mixed states, it's a monotone. It's a magic monotone. Yeah. Yes. Yeah. So there's Inlin developed a very powerful Monte Carlo with sampling method. Yeah, it was. Yeah. Yeah, there's no sign problem. Yeah, so this is a trivial gap space. I will just use maybe 5 or 10 minutes to finish everything. Okay, so this is more non-trivial one. It's a gapless as people call intrinsic. It's heavily discussed in these papers, but the idea is there's a non-invertible symmetry. Basically, I have two kind of spin. One is tau, another is sigma. But if I don't do this KT transformation, it's just like if you look at the tau degrees of freedom, it's just a XX model, which central charge is equals to 1 theory, gapless. If I look at the sigma part, which is the ZZX, which is just the Ising model, it's gapped base, only has transition when H equals to 0.5. And then there's a way you intertwine tau and X degree, tau and sigma degrees of freedom by this non-invertible KT transformation. And it's called the intrinsic gapless SPT because you cannot cook up this model from any known gap SPT phase. There are some mathematical structures, but what I'm trying to do is I'm trying to use my Pauli spectrum to see this. So if I look at the, and there's people already know what is the associated Pauli string or SPT string non-local parameter associated with this intrinsic gapless SPT. Since it's gapless, it's not scaled like older one. It has a power law decay form, like a critical phase with some conformal weight. Anyway, so as you expect, M2 cannot distinguish two gapless phase. So this is gapless for H, for arbitrary H, or for H greater than 0. But there is a transition between two gapless phase. So specific at H equals to 0.5, because as you know, if it is if it is not 0.5, then I have a XX model, which is central charge 1. But at H equals to 0.5, I add this point Ising CFT on top of this central charge 1 CFT, so it becomes like a 2/3 CFT. So there's a transition happen. You see there's a transition from M2 for this gapless space, two gapless space. And then just showing this Pauli string has Pauli spectrums has a way you see there's a duality transformation. And this duality transformation is basically from this non-invertible one. Okay. So I will just use 5 minutes to, and I just want to, it's just like things that I have done in my PhD. Yes. 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 Sorry, not this one. Yes. One half charge gap in both space, but it's still like a gapless SPT phase because there's some symmetry protected boundary state even in the gapless phase. So that's and it has nothing to do with gap phase. Yeah, because it's purely from this XX model term, which has additional decoration on it. Yeah, it's a very, very exotic many-body phase, but what I'm trying to show is maybe this stabilizer entropy or their distribution of spectrum can show some interesting property. As I show in here, there's a duality transformation. Anyway, entanglement also have disclosing, and then there's something like a supersymmetry quantum mechanics associated with it. That's what I did in my PhD. So I just somehow this spirit comes from my very early careers of my research, and then transits to this Pauli spectrum. So I just want to show here. And then the remaining few minutes, I will just talk about how I can generalize this SRE to bosonic systems, because previous this stabilizer states people discuss are for specific for this spin system, but in principle we can generalize into a spin system, and then we can consider hybrid spin boson system. So the idea is we just need to find some analogy between these two. So spin and boson, so computation basis we know. Pauli group, we can use this Heisenberg-Weyl group, so mathematical there is a very similar structure, Clifford group, Gaussian unitary, and then stabilizer state, which is very effectively simulated by classical computer. So in terms of boson system, Gaussian state are very cheap, easy to understand. So there's a very one-to-one analogy, so we can use the same definition to define the associate entropic measure, which we call the Gaussian Renyi entropy. So the distribution from the Pauli string will replace by this Weyl function. Basically, we just replace this Pauli string by displacement operator for boson, and you can evaluate this quantity. I'll just flash everything. So this is the standard entropic measure, and then you can extend it to the hybrid one spin and boson one. You can just put this in this form and then evaluate everything. So just give you example. So this is just a fork state, 0, 1, plus, minus. So 0 is just a Gaussian state, so it must be 0. 1 is not a Gaussian state, you get this value. There's some property for the Fock state. You can use an harmonic oscillator as an example. So when lambda is 0, it's basically a Fock state, a Gaussian state, but with this harmonic, then you can introduce non-Gaussianity. So we show this, and this Gaussian Renyi entropy will be 0 when lambda goes to 0, and then increases with non-vanishing lambda. Both-Haber model, we can do the same thing. The thing we are more interested in is this hybrid magic entropy, because in quantum optics or in some platform of quantum computer, we have a boson coupled to two-level system. So this is the Dickey models, but people know there's a transition from novel to super radiant. Then we can use this hybrid magic entropy to see it's peaked at the transition to observe this kind of phase transitions in these hybrid spin boson systems. We can also study the dynamics of these spin boson hybridized systems in terms of the dynamics of all this quantity. So idea is we want to see how the quantum resource shared by the spin and the bosons using these quantities. And then I give a quick final remark. So after we finish this thing, I want to apply to CFT because there's a papers before by Ashida's group, but this is their old paper. I want to apply our GRE to the conformal field theory because they find the SRE, the spin part, there's some kind of constant term which corresponds to the G vectors, which is the boundary CFT kind of data. And then soon later we published the paper, they also extended to the non-Gaussianity as well. So just a remark, this is very useful. So if you want to study the CFT content, then there's some universal CFT data you can obtain from this quantum information measurement. Okay, so I just leave my conclusion here, and then thank you very much for listening to my talks.
Questions?
Yes.
Can you remind us, like, what's the resource-free operation?
So it's a Gaussian unitary increase squeeze operators, and then let me see.
Physically, is it doable or like?
Yeah, you can have. It's doable. Like a squeeze operator, I think it's doable. Just change the size of your harmonic. Like you have like a exponential a square, a Dagger square minus a square. Something like that. I think people can create do a lot of optical things, and then they can exactly measure the Weyl functions of quantum optics. Yeah, so I think people already know this in quantum optics, and then people use Wigner quasi-distribution functions to associate with all of this. Just as you know, this quasi-distribution function also can be classified as a quantum resource. Yeah, so this is just a different way to measure this quantumness or quantum resource. Yeah. Yes.
Question on the GSPD example.
Okay.
That you show that the M2 is symmetric, right? Because it's
G. Okay. Yes.
So is the duality related by Clipper circuit up to projection?
That's what our observation. I don't have because this is all. So this duality basically evolved the Clifford gate. Some kind of.
This is mapping Pauli string.
Yes. Yeah. Exactly. Exactly.
Roughly implemented by Clipper and you have to have strength.
Yes. Yes.
Multiplied by the
Yes. 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 Yes, yes, that's what we see. Also, you can see from the M2 because it's symmetric, so it must be, yeah. But we just show it example by example. We have 3 examples. I only show 2 here, but I think, yeah.
What do you mean by topological?
Oh, sorry. This is a type. This is the CFT, which is trivial, and this is the topological. This is the CFT where there's a boundary. People call it a symmetry enriched criticality, something like that. Yeah, this is a non-trivial gapless space. And then there's a boundary between the trivial gapless space and the non-trivial gapless space.
Do you understand why the 3-half CFT?
The 3-half, it naively understand is this is the XX model, so central charge is 1, and this is just IC model. It's the so it's just added.
Any questions? If not, let's send speaker again.
Yeah, thank you.
Yeah. Let's back at 3 p.m.